Buenas tardes. My name is Anna Korczak and I came from the same university. We, as was said, work in the same department. And thank you for giving me opportunity to give this presentation here. The title is Application of the Fluid Concept Method to Transfer Problems in Biological Tissues. So will be a lot of mathematics and the presentation will be actually shorter. So my agenda, a short introduction, why we analyze biological transfer, and then I will present different mathematical models. They are in order from the oldest one model, the Cannon equation, then the Cannon equation, the dual-phase equation, and the three-phase equation. And here in parentheses, you can find the official date when this equation was created. In the next point, I will tell a few words about the finite quantity method. It will be an example of the application of this method to dependence equations. So this, let's say, the easiest one. And in the end, I will conclude my presentation. So the unit transfer models developed nowadays are fundamental component that supports medical applications, leisure therapies, surgical procedures, and here should be mentioned also about the oncology. These equations incorporate various factors such as blood perfusion, metabolic generation, thermal properties of tissues. There are the most basic ones. Those parameters we can find in Canon's equation. By considering the model as transient, it is possible to capture the temporal and spatial variations of temperature, distribution accurately. And they allow to analyze the influence, for example, laser irradiation, and this process model based on the Weber law, which relates to the attenuation of the laser energy as it penetrates through the tissue. And this factor is very important for understanding of how laser energy is absorbed and converted into thermal energy. In some more advanced models, we can consider perfusion rate and effective scattering coefficient. That depends on tissue injury. And this shows the dynamic nature of tissue response to laser irradiation, generally on heating, where changes in blood flow and tissue properties can accrue due to the thermal damage. And selective modeling can allow for more realistic representation of the changing thermal conditions within the tissue. And we can create more complicated models. So now another step is getting more advanced models like two-phase lag model or three-phase lag model. We can introduce lags. And for example, in two-phase lag model, we introduce lag in temperature gradient and heat flux. And of course, we are improving the accuracy of the results. And those models are especially applied when we analyze rapid thermal changes, studying microcircuit transfer, and also in nanotechnology, cryogenics, or consider high frequency thermal waves. Okay, so let me start with the Canon's equation. This equation directly bases on the Fourier equation. I have no Fourier equation, so we can see that they are very similar. And but what is crucial, of course, all parameters we can specify for example, in tissue if we analyze. So, like the volumetric specificity, the thermal conductivity we must put specifically for skin tissue. What next? We have three heat sources. Two of them we must analyze one's optional. It is this heat source connected with the laser irradiation. But the heat source connected with the blood perfusion and the metabolism is like getting something like 1-3 independence equation. What more? Generally, the heat source connected with the metabolism, the constant value, but exists some models when we can analyze it as a function, but normally in most of scientific papers we can find a constant value. And the heat source connected with the perfusion, we define as a function that depends on the temperature of the skin tissue, and we have two more parameters. The blood perfusion and the volumetric specific heat of blood. We can analyze them in a basic of a constant value, but of course we can make our model more complicated, more accurate. So we can define Bernoulli heat source function with the blood perfusion coefficient defined as a function. This theta, this parameter, is an Arrhenius integral integral. So this function depends on this, it's some kind of polynomial. As I said, it's an integral, so we can see here this parameter. It depends on temperature, some other constants that we can see explained in the table before. And those all parameters here are like are presented average parameters for skin tissue. But we must remember that we can analyze multi-layer skin tissue, for example, that at least 3 main layers. So those parameters will be changed. These parameters are like average for 1 layer skin tissue. What next? Heat source that is optional, so laser heat source. Here we have 4 parameters. The attenuation coefficient and laser maximum peak power. And also we can make it more complicated. So the attenuation coefficient can be also dependent on the Arrhenius integral integral. Generally, the attenuation coefficient is a sum of the absorption coefficient and the effective scattering coefficient, and the second of them here defined can be a function of the integral. So why we put those all parameters dependent on the Arrhenius integral? It's because the tissue is changing when it is getting hotter. It is in one point it is getting burnt, and then all parameters are being changed. And what is maybe worth to mention here also, okay, here you can see that for theta more than 1, we have this parameter equals to 0. And normally theta equal 1 means totally burned tissue, and it's end of our analysis. But we can find some scientific articles where more than 1 also is analyzed as a parameter. But generally 1 is the limit. Okay, so the next model for the Bernoulli equation looks like that. What's the difference between Bernoulli and Bernoulli equation? We have 1 additional component and also 1 additional parameter. So the relaxation time, it is time delay for heat flux response. This seconds. And what does it mean for us if we want to solve this equation? For example, when we use finite difference method, we must put into our formulas not only one step before, temperature for one step before, but also another one before, so 2 steps before. We must always keep in our memories calculated. And the dual phase lag equation. So also the difference now between Casanova and North and the dual phase lag model. We have 2 more components and also one more parameter, the thermalization time delay for temperature gradient. And we also in this model have second derivative after time. So also when we want to solve it, we must keep in mind 2 steps before. But temperature for 2 steps before. And rather new in scientific researches, the 3-phase lag equation, much more complicated. And here we have, being honest, 2 more parameters: the relaxation time delay for thermal displacement gradient, and also I didn't mark it, but the rate of the thermal conductivity. So this equation, I put it rather, let's say, some kind of shortcut, because, for example, Q, it means those 3 components here summed together. And as we want to analyze it like before, so to see differences, we must multiply it. So it looks more like this. And here are marked also some differences. So appears derivative of the 3rd order. We don't have derivative after derivative of the 1st order. We can say that it compared to the dual-phase lag equation, it has changed. So we had before here second derivative and here first. This part is the same, but here also appeared some new things, like with lambda rate of the thermal conductivity. And here also we had before no derivative, and here was first derivative. So it has changed. And now about the finite Korczak method that can be applied among some other methods. So here is sitting the specialist of this method, so I hope I will not commit errors. So this method is a local iteration process. It is based on the so-called moving squares procedure, and function and its derivatives can be very closely approximated at an arbitrary point from its discrete values belonging to the surrounding cloud points. The main idea. The FPM has been already applied in the fields of fluid mechanics, radiative heat transfer problems, heat conduction, and some other also. And how does it work? So let omega be a given domain with a particular boundary, and suppose that the set of points x are distributed with the corresponding fraction values t. And the problem is to find an approximate value of t at an arbitrary location x. So to do this, let's define the approximation of t using the Taylor's expansion around x. We can see it here. This is expansion for 3D problem, the most general problem. And this Taylor expansion we can write in a vector sense, so it's the same, but using the vectors. And the unknown vector b, so this vector is obtained from a weighted least squares method by minimizing the quadratic form that we can see here. When we take into account only neighborhood points of x, we consider Gaussian weight function, which is here in our quadratic form. And the minimization of J yields vector B. Vector B is recalculated during some iterations. Where matrix is W is defined before, it contains weighted Gaussian functions, and matrix P and vector A I have here. So this matrix P has some differences, and the last row depends on our equation. So here is presented last row for the Fairness equation, for example. But if we consider a different equation than comparable or well-phased equation, then this last row will be changing. And the same with the vector A. We have temperature in neighborhood point, and the last element of the vector A will be changing depending on the equation. And this is matrix P of vector A for the x when x belongs to the integral part of our omega. And if x belongs to the edge, so for example, satisfies boundary condition of the second type, we have one row more and also one component more in vector A. The same situation if it's a boundary condition of the third type, but of course this row and this element will be different. If we have boundary condition of the first type, we can apply the same approach, or also we can just put in an arbitrary way those temperatures on the boundaries and just not recalculate them. Just use them to calculate temperature of other points, but we don't calculate them. And in the end, some general conclusions. So some practical problems that can be solved using biologic transfer modeling, the analysis of skin tissue burns, the analysis of tissue heating subjected to external electromagnetic field, the evaluation of thermal damage of biological tissues caused by laser irradiation, the identification problems such as the location of tumor, the estimation of degeneration rates in living tissues. And as it comes to the tumor and oncology, there can be created more tasks to solve. And also another thing, if you want to make more complicated those models, we can, for example, use interval arithmetics or quasi-arithmetics. So we can treat some values as not adequate, so we can put an error on them, but it could be another lecture. Thank you very much.
Thank you for the. So now, los la cuestión por profesora Ana.
Have you put some approximation with that model?
Yes, but I didn't want to make it no longer, this presentation. So much mathematics. Yeah, but yes, I was studying one-dimensional problem, the Fairness equation, and with the single valued numbers, and also with those that I mentioned, interval values and fuzzy numbers. And also 2D projects I saw, but it's not already published.
Okay.
But the results would satisfy me because compared to some other results to from the literature they were. Yes.
Okay.
Thank you, profesora. Does only have another question? So,
Okay, that's too much mathematics.
yes. So, Professor Anna and Professor Valdemar Muchat, we would like to say thank you for your presentations here. So, I will read the certificate of participation in this seminar. So I will read. Some parts are in Spanish, some others are in English. So I will read it as if it is in here in the document. So, Universidad Autónoma de Coahuila, Centro de Investigación en Matemáticas Aplicadas, Cuerpo Académico de Computación Científica y sus aplicaciones, Programa de Maestría en Ciencia de Datos y Optimización, IPS, Certificate of Participation, to Professor Valdemar Musha and Professor Anna Korczak, who successfully presented the talk titled Evolutionary Optimization in Structural Mechanics. And application of a meshless method to heat transfer problems in biological tissues. Since doctora Irma Delia García Calvillo, directora del Centro de Investigación en Matemáticas Aplicadas, on September 12, 2024, Saltillo, Coahuila. So, thank you, professors.
Thank you very much.
Support. Some presents for you. So this is a small present from university and Dr. Irma.
From Vanessa.
Vanessa gives you this.
Thank you very much.
So thank you, Professor. So to finish, we would like to express our sincere thanks. First, to be here with us as visitors, professors, and also by your support giving this seminar to our students. So thank you very much.
Thank you. We would also want to express our gratitude. It was our pleasure to be here. Our research stay at the university is coming to an end, but it was very interesting experience. We have learned a lot. It was a pleasure to be working with you. And if someone from this room was interested in any cooperation in the future with us, if the topics were interesting for you, then please contact us. I forgot to put my email address on the presentation, but maybe if you are interested, Professor Felix could give you our contact, and we also invite you to Poland to visit our university. So thank you.
We will go. So thank you. And thank you to the attendants for being here. We close the seminar with this. So thank you so much.